So today we are interviewing Sanjit Seshia of UC Berkeley, who works on formal methods with applications in cyber-physical systems and security. And so Sanjit, could you tell us a little bit in general terms about your work and the relationship of Boole's work to it?
Yes, sure. So it's actually a pleasure to participate in this project. My own research centers, as you mentioned, on an area called formal methods. So let me start out by telling you a little bit about that area. So formal methods has roughly three major components, three major sub-areas. Specification, which is the area that studies how you mathematically specify what a system, such as a program or a circuit, is supposed to do. And then the next is verification, which is to algorithmically verify whether the system indeed satisfies its specification. And then the third subtopic is synthesis, which is to automatically, algorithmically synthesize the implementation of a system from a high-level specification. And so formal methods broadly comprises these three topics: specification, verification, and synthesis. But at its core, the essence of formal methods is really computational proof techniques. And so it's all about proof. And I think it's this core which has the most direct connection to George Boole's work. So in particular, Boole was one of the people in the mid-19th century to attempt a formalization, a mathematical formalization of logic. And in the process, his work on symbolic logic, I think, through its various threads over the years, has had a big impact on formal methods. Because logics are really some of the most common and also effective ways of specifying properties of systems and building models of systems. So that's been one direct connection of Boole's work on my own work. But there have been other connections that have gone a bit more deeper. So as you also mentioned, the applications of my work have been to topics such as cyber-physical systems, which are computational systems that are very tightly integrated with the physical world around us. So examples include modern automobiles, which have a lot of software controlling various aspects of the automobile. But then their primary purpose is to control fuel injection or control braking or control steering and so on. And those are physical processes. So this is actually it's an old area, but it's only recently become something that's come together as an intellectual discipline. And logic, again, is at the core of it. Computer security also has had a lot of influence from logic. And I've also worked on electronic design automation, so tools to design circuits, computational tools to design circuits, as well as more recently applying very similar techniques to synthetic biology. And again, at all of these, computational proof is very much at the core. So my own rather deeper personal connection to Boolean methods goes back a bit more than 15 years when I was a PhD student at Carnegie Mellon University, working with Professor Randolph Bryant. And at the time, this was about the year 2000, there was a lot of excitement around advances in a problem called the Boolean satisfiability problem. The Boolean satisfiability problem is one of the most celebrated and central problems in computer science. It's the canonical NP-complete problem. But it's also a problem that is really important from a practical viewpoint, because a lot of important engineering problems and practical scientific problems do translate down to Boolean satisfiability, or SAT. Just for our viewers, the Boolean satisfiability problem is the problem of given a Boolean formula or a Boolean circuit, if you want to view it that way, which is a combination of standard gates like AND or NOT and so on, and it's a function over n input variables, and they are Boolean. They can take values 0 or 1. The question is there an assignment of zeros and ones to the inputs such that the output is a 1? And so this problem has very direct connections to problems of checking correctness of circuits. And indeed, that's a place where it's had a lot of impact already. But back in the year 2000, Boolean satisfiability solving was still considered a hard problem even in practice. The solvers weren't very efficient just yet. Some of the most effective techniques for Boolean reasoning were based on a data structure called binary decision diagrams, which was invented by my advisor, Randy Bryant. And so, BDDs, as they are called, had already a major impact on the industry. And SAT solving was just, people was just starting to revisit it. And what happened was there were a couple of researchers at the time, around 2000, who came up with some very clever ideas. And that really started a fresh wave of advances in SAT solving that made them much, much more efficient and fast in practice than they were previously. And so as a graduate student at Carnegie Mellon, I was observing this, and the thought came to me and my advisor and some of my colleagues that, given the advances in SAT solving and Boolean reasoning that we now are starting to see, what can we do about more richer classes of problems? And by richer, I mean that the Boolean satisfiability problem is one where the data types are very simple. Right? It's just the values that variables can take are Boolean, 0 or 1. But a lot of problems in practice, such as those that arise in rich programming languages, start from an input that has a lot more richer data types and a lot more expressive data structures. And you could, given that everything is finally implemented on a digital computer with a finite amount of memory and so on, you could ultimately, as they say, blast everything down to bits and encode your problem in Boolean satisfiability, but it would be way too inefficient. And so, the common way to encode it would be using some collection of logical theories. And so there was already, for a few decades at the time, there was an area of automatic theorem proving, which had a lot of work on it already. But the work on automatic theorem proving had not yet been connected to the advances in SAT solving. And so this connection of between automatic theorem proving and Boolean satisfiability solving became really the core direction for my thesis work. And so it turned out to be a very fruitful connection as well. So we then started out to see how we can make a connection between the field of automatic theorem proving and the advances in Boolean satisfiability solving. And in particular, the idea was that perhaps we could take the input problem for the theorem prover and then, through a series of transformations, reduce it to an input problem for the SAT solver, a SAT problem. And so this resulted in a system called Euclid, which is both a verification system, a modeling and verification system, but also at the back end has a solver. And at the time, we called it SAT-based theorem proving or SAT-based decision procedures. But over time, the area has come to be known as satisfiability modulo theories, or SMT solving. And so Euclid was one of the first of a collection of SMT solvers, all of which the first papers all came out around the time of 2001, 2002.
Could you tell us a little bit about how the transition came from one to the other, the intermediate steps to come from the theorem proving to the...
Absolutely.
Thank you.
Yes. So, at the time there were many ways of translating, and even now there are many strategies of translating from an input problem that's in some collection of logical theories, richer than propositional logic, to propositional logic. And one approach was to take an approach very similar to a compiler. That is, you take your input problem, which is in a collection of theories like equality and uninterpreted functions or linear arithmetic over the integers. And you translate that using properties of those theories. You translate that to a propositional formula such that the translation preserves satisfiability. That is, the final propositional formula is satisfiable if and only if the original formula in the collection of theories is satisfiable. And to do this, you would use various properties of those underlying theories. For instance, for the theory of equality and uninterpreted functions, there's the congruence axiom, which says that if you have two functions f and y, if you have two variables x and y, and you have a function f, then if x equals y, then f of x equals f of y, right? Very simple, intuitive thing which just defines what a function is, right? You could encode that in a way that transforms away the function and turns it into a resulting representation without any function symbols. And you can take that representation without any function symbols and encode it to a SAT problem by choosing an appropriate domain over which to interpret all the variables that show up in that. This is called the small domain encoding. And so it exploits a certain small model property of the underlying theory. And you could do this, we showed that you could do this not just for equality logic, but you could also do it for a slightly more complex logic called difference logic, where you can write things like x minus y is bigger than 10, right, some constant. And then we showed how you can extend that even all the way to full linear arithmetic, where you could write, 5x plus 3y plus 7z is greater than or equal to 100. And so we used a series of theorems where you could show that in all of these cases you could encode it as a SAT problem with only a polynomial size blow up in the encoding. So the SAT problem would be polynomial in the input size. Overall, the most important features like the number of variables and the numbers of constraints, and that was pretty important. And so, and then ultimately, even as we were doing this work, SAT solvers were getting much faster. So at the time, and even today, when I teach a class on formal methods, I go back and update a slide that I maintain, which is to show the advances in SAT solving since the year 2000. On a set of benchmarks that I care about. So I don't claim that this is something that is general enough for all SAT problems, but for the problems that actually were generated using the Euclid verification system, I go back and revisit how much better SAT solvers have got. And at the beginning, this is in the year 2001, 2002, 2003, the improvements were dramatic. We got something like a 100x speed up in SAT solving. What's actually remarkable is even today, so this is almost 15 years after those, we are still seeing about a 1.2x improvement in the speed of SAT solving, at least on these benchmarks that I care about. And I think that's very promising, because it's saying that there's still potential, that people are still finding very creative ideas to improve performance of SAT solvers. It's largely driven by a lot of very interesting benchmarks with practical applications. But the continuing improvement seems to indicate that the strategy of doing theorem proving by translating to SAT is still a good one. And so that basically the way we thought about that was that these are Boolean methods for theorem proving. When I gave talks about this back in 2005, I would say that this is essentially verifying or reasoning about systems using Boolean methods, because after all, what we're doing is we're taking an input problem that's much richer and translating it down to Boolean logic, right? And using very simple proof rules to reason about the resulting encoding. So So that, I think, was one connection, a deep connection to George Boole's work. And another thing, actually, that Boole did back in the mid 19th century is think about doing logical reasoning using algebraic methods. So, the idea of algebraic simplification and so on. And that, I think, is another idea that has grown and endured, and it's at the heart of a lot of most effective theorem proving methods, and even, I would say, more broadly, verification techniques. Because I was just talking about SAT solving a while ago. Some of the most effective recent SAT solving methods in the last 5 years or so, in the recent times, are actually based on doing rewrite rules, at various stages of the SAT solving process, the pre-processing and then what they call in-processing and so on. And I think the genesis of these rewrite rules, in a way, goes back to this idea of using algebraic techniques to do logical reasoning, then think about writing equations and simplifying equations and so on. So I think that's another thread that goes all the way back to Boole. So even today, I mean, that all of this work on Euclid that I mentioned started back 10 odd years ago. And we continue that thread of work in my group still today. So Euclid is still being extended. The field of SMT solving has become more mature. It's to the point where people now rely routinely on SMT solving to do various logical reasoning techniques and proofs and so on in other applications like program analysis or software synthesis or finding security vulnerabilities in software. And so there's lots of other applications that have come to build on the notion of SAT-based theorem proving. And I think, so now, for instance, some of the things we're doing with Euclid are to tackle problems in security, trying to, one of the big challenges in computer security is how can you design a piece of software or hardware that forms a trusted computing base or TCB for the rest of the system, and you want to formally verify that it indeed satisfies certain key security properties. And this has proved to be a very hard problem. And so, we've been tackling this along with colleagues in the security and systems area, using Euclid as a vehicle. So I see this as, there's still a lot of challenges left to drive the progress on reasoning based on Boolean methods.
So Sanjit, if you would try to explain to undergraduates by example what you could cover in those logics that you mentioned, how would you go about it?
Sure. So let me assume to start with that this is undergraduates in general, not necessarily computer science. So one logic I mentioned was this logic called difference logic, where you can write things like x minus y greater than or equal to some constant. Using this logic, you can express ordering constraints between events that have to happen. So think about class scheduling, right? So in class scheduling, let's say you're trying to build your own class schedule, and you can think of every class that you want to take happens during some day of the week. It has a start time. You call it let's call that SI, and then the end time EI, right? And it has a certain amount of time. And so you may write a constraint like EI minus SI is equal to 2 hours, if it's a 2-hour lecture, right? And there may be another class J, where you have a similar constraint. But of course, if you want to take both classes I and J, then you have to make sure that the intervals don't intersect. That is to say that Sj doesn't happen between Si and Ei, right? And so you can write constraints like, Sj is you'd rather, actually, what you should write is the end of the class J should either be before the beginning of class I, so Ej is either less than Si or Sj is bigger than Ei, right? So j happens after course I. And so these sorts of constraints can be written in difference logic. And indeed, scheduling problems are sort of naturally encoded in difference logic. Okay. Okay. So if you're a computer science undergraduate, then certainly you've taken classes in programming languages and introduction to programming, for instance. So let's say, assume that you're programming in a language like C or C++, and you're writing a program that computes a function of its inputs. Okay. So let's say a program that computes factorial of some number. The way a lot of students test their code, and actually a lot of instructors also grade student assignment these days because of the large classes, is to run a bunch of test cases. You test your program on a set of inputs, and if it seems to give the right answer on those, then you're happy. But imagine that you wanted to do something more detailed. That is, you actually wanted to check that for all possible inputs, the program computes the right answer. Now, this is a problem of checking equivalence of the outputs of the program, of the candidate student program with the instructor provided solution. And for a programming language like C or C++, the data types are actually finite precision. So even though you're computing factorial of a 32-bit quantity, for instance, right? So the output is a 32-bit quantity. And so in principle, since everything is finite, one can translate this down to a Boolean satisfiability problem, right? But it turns out that that's sometimes not the most efficient thing to do. And so there is a logic called bit vector arithmetic, which naturally encodes the operations you have in a language like C. So you have addition between 32-bit quantities, you have subtraction between 32-bit quantities, you have division, you have bitwise operations, and so on, and all of these can be encoded naturally in bit vector arithmetic. And so you can actually build autograders for programs over finite precision types that compute functions of their inputs based on an encoding into bit vector logic. And so I should point out bit vector arithmetic is one of the most effective and widely used logical theories within the SMT solving world today. So those are two examples of richer theories that both of which have effective encodings to Boolean satisfiability, and in fact I would say most theorem proving techniques for those logics, if not all, are based on a reduction to SAT.
How would you view Boole's impact on modern society, in particular with respect to SAT solver applications? Or
sure. Yeah. So I think Boole has had a huge impact on modern society, and I think it's come from one of the major places it's come from is the use of software tools for design automation of computer chips. So one can make the argument that modern society increasingly is running on microprocessors and other computer chips, and the design of these chips relies on a slew of tools, software tools, that help people automate various tedious aspects of the design process, all the way from a high-level design down to synthesizing a gate-level circuit, and then a transistor-level circuit, and then something that would then be shipped out to the fab in the form of a mask, and so on. And one of the key problems when you compile a high-level description down to gates and transistors and so on is you want to make sure that what the designer coded up in a high-level programming language, a hardware description language, is indeed what is being fabricated. Right? So we have this problem of checking equivalence between the original description and the final description. And this equivalence checking problem at many of these levels, not all, but many of these levels, reduces down to Boolean satisfiability. So for instance, if you had a synthesis tool, a logic synthesis tool that took in Verilog or VHDL code and then generated an optimized gate level representation in terms of the gates that are available in a particular technology library, then the problem of checking equivalence between those two levels is basically a SAT problem. And equivalence checkers are the workhorse of EDA tools, electronic design automation tools. They're one of the most effective applications of formal methods to industry. And in particular, I wouldn't say SAT solving is the only technique that's used in equivalence checkers, but it is one of the key techniques that's in there. Another key technique that's in there are logical rewrite rules, so simplification rules, and those that are in the SAT solver as well as those that are separate from the SAT solver, and those are also very important in the design of equivalence checkers. So I think there's an indirect major impact that Boole has had in terms of the ideas that he propounded in the 1800s, leading to ideas that have gone into logic synthesis and equivalence checking. And those tools are central to the design of computer chips. And of course, computer chips, I think, in a sense, are the bedrock of today's society.
So Boole is named as one of the founding fathers of computer science sometimes, or information technology, and I wondered what your view might be about that.
In a way, yes. I think it's fair to name him as a founding father of computer science. There are many ancestors, I think, I should say, for the field of computer science, and certainly I think the list would be incomplete without Boole.
What would you consider Boole's most significant achievement?
Right. So I don't consider myself much of a historian, so I should say I don't know to adequate depth about all of Boole's achievements. But I do know from reading that he is one of the mathematicians credited with the formalization of logic as a field of mathematics. And I think just that, just the contributions that he had in the mid 1800s to mathematical logic, those have, in the form of symbolic logic, right? Those have really had a major impact on computer science and certainly my own field. There's of course also the idea of an algebraic approach to logic, which I believe he and his descendants had a big impact on. So I think that's another really important contribution of his work.
Is there an achievement he might need to be better known for or should be better known for?
That's an interesting question. So in reading up about Boole recently, I realized there was a connection that I was not directly aware of, which was that he was one of those who made a connection between logic and probability. And this is actually a very exciting connection, and one that has had less attention in computer science in the past, but now I think there's an increasing interest in this connection between logic and probability because of the rise of probabilistic techniques in areas like machine learning and AI. And this connection between logic and probability is showing up in an interesting place these days in the areas of cyber-physical systems that I work on and in fields like robotics. You build systems that interact with the physical world and with humans, I should say. And one of the interesting aspects of this interaction is you don't know all about the world around you when you design the system, right? And there's a lot of uncertainty. And probability is one way of capturing that uncertainty. And at the same time, you're actually you're designing software controlled systems, formal artifacts, which are nicely encoded in logic. And so what at least I'm seeing in some of my applications is that there's this very interesting scope for looking at the marriage of logic and probability in sort of practical applications. And people have done this in many areas of computer science already, but it was interesting for me to go back and see that some of Boole's work touched upon this connection between logic and probability, which is really neat.
Could you hazard a guess of what Boole's contemporaries or Boole himself would have thought about all these applications that are still ongoing?
I find it hard to speculate about something like that. The one thing that I will say about this is when I read biographies of scientists or mathematicians or computer scientists, I'm struck, or even interviews of computer scientists of our generation, I'm struck by one thing that they tend to say, which is that they never expected the applications of the theories or the initial work that they did. And so, it's hard to say what they would have imagined of all the various the applications of Boole's work that has come about. Boole was there where he was in the mid 1800s and made his contributions, and that has had a big impact. It's hard to say what if he hadn't been there. Chances are there may have been another mathematician coming along to make those contributions, but all of this is just speculation. So personally, I'm glad that Boole made the contributions he did, and we've been benefiting from all of those.
How long do you think Boolean algebra or Boolean circuits will be taught towards the future?
It's hard to predict these things because curricula do change quite a bit over time. But if it were left up to me, I feel Boolean algebra and Boolean circuits should remain a core component of certainly undergraduate, lower division undergraduate curriculum in computer science and related areas like electrical engineering. Personally, I first learned about Boolean algebra in the formal sense in high school. And in fact, one could argue that the place of learning some of the basics of Boolean algebra should be in high school. It's really, computing has really become that fundamental. As Jeanette Wing says, the computational thinking is really something that pervades society these days. And so I think children in school would benefit from learning about these very fundamental ideas.
I'd love to hear some more about, you mentioned BDDs at the start, binary decision diagrams, and then a shift later on as well.
Yes.
How much would they, because BDDs are really a data structure that captures Boolean expressions in an efficient way.
Right.
So I was just wondering how much of a role are they still playing? Are there shifts in that, or what's the evolution?
So I think BDDs are still a very central component of electronic design automation tools. There are, I hear from industry collaborators that there are still problems that cannot be solved by SAT solvers and are solved efficiently with BDD-based methods. But I think one thing that's more important to understand is that even though BDDs were originally, I think, in the mid-90s, they were one of the killer apps was equivalence checking for circuits. The BDD data structure was way more than just an equivalence checker, right? Because the BDD captures not just one satisfying assignment, but all satisfying assignments. Whereas the SAT solver is just looking for one. So recently there is an area that is emerging for which I believe BDDs may yet find a nice niche application, and this area is the one of model counting. That is, counting the number of solutions of a satisfiability problem rather than just finding one. And a related problem is that of uniform random sampling or sampling solutions according to some distribution. So for model counting, once you have a BDD, it's fairly straightforward to count all the solutions by walking the data structure. And this has been well known. And so recently there are areas that where this sort of an approach to counting the number of solutions could be quite beneficial. For instance, in computer security, there is a problem called quantitative information flow analysis, where the idea is that you have some secret, and then you have some data that's written out to a public channel, like a network socket. The program has a secret, like a secret key, and the question is, can the secret, the value of the secret flow to that public channel? So this is just a Boolean question, and in many cases the answer is actually yes. Some secret information can flow, but the question is how much, right? So for instance, think about a password checker, right? Suppose there is a server that has all the passwords, and then there is an attacker who's trying to figure out the password to let's say Alice, and so the attacker is trying to masquerade as Alice and supply the candidate password, right? Now, if the attacker sends some arbitrary password to the server is going to respond back with one bit of information about the real password. That is the real password equal to the one that the attacker sent or not? Right? So one bit of information about the secret password leaks to the attacker. But that's okay, because from a cryptographic standpoint, the attacker would have to do an exhaustive analysis of all possible passwords before he or she is able to get at Alice's password. So really, one of the questions is how many bits are leaked? And it turns out that you can actually reduce this problem down to, at some level, the problem of counting the number of solutions to a satisfiability problem. Very similar to the way in which a problem of checking whether or not there is a flow could also be reduced to just a SAT problem. So that's one practical application of model counting. I see BDDs as something that are still, for exact model counting, they're much better than SAT. There's actually interesting advances in approximate model counting, which are based on SAT. So it's sort of an interesting interplay. And those approximate model counting techniques ultimately rely on an exact model counter at the core. So I think BDDs still will have a lot of applications. And one of the key things about the BDD, of course, is that it's a canonical data structure for Boolean functions. So any application where you need a canonical data structure to represent a set of something, there still is no better data structure than the BDD for that. So I think these are SAT solving and BDD are I teach them both in my courses. I think they're both essential tools in the Boolean methods toolkit. There's a connection. There's some sort of a historical connection in a way. I mean, this is something that I'm speculating about, but of course, one of the things that BDDs, one of the rules that BDDs are ultimately fundamentally based on is Shannon decomposition, right? So, Claude Shannon was influenced when he came up with switching algebra. He was influenced by Boolean algebra, which of course was not exactly what Boole had formulated, but it was a descendant of the work that he did. So in a way, I mean, there is if you wanted to trace a path, there is a historical path from Boole's work to Shannon's work and then to BDDs.
So Sanjit, what would be your view of teaching Boolean logic, maybe even beyond computer science, in other contexts, at high school level or in other ways?
Okay, so that's a very interesting question. So let me mention two personal experiences, one as a student and the other as an instructor, which goes beyond the teaching to a computer science undergraduate audience on campus. So the first experience, which I mentioned briefly in relation to another question, is my own. When I was a high school student in Mumbai, in India, and this is perhaps equivalent to 11th grade elsewhere. And at that point, at least back in Mumbai at the time, there's a little bit of a specialization that occurs where some students take special courses in electronics or computer science, and other students may focus more on biology with a view in going into a medical career and so on. and others may go into social sciences. And I chose the electronics and computing related stream. And there I was exposed to some of the basic ideas in electronics, which come down to Boolean algebras, the laws of Boolean algebra, simplifying Boolean equations, and then implementing those as Boolean circuits. And we learned a little bit about how you could implement them with relays and vacuum tubes, and then transistors, and then the more modern VLSI technologies. And so I think that was one of my first sort of direct exposures to Boolean algebra and Boolean logic. And I believe, I'm not completely sure, but I think that form of teaching Boolean logic still exists today.
Would you say that it influenced your choices later on of what you studied?
In a way, yes. I think I really enjoyed it. I have to say, in 11th grade, I really enjoyed all the exposure to electronics. And before that, I loved mathematics. And so I think the combination of the two led me towards computer science and engineering as a career. And so, yes, I think I was very positively influenced by my early exposure to Boolean logic. So that's the story as a student. Now, as an instructor, I have mostly taught to audiences that are in computer science or electrical engineering. But last year I had the pleasure of teaching one of these massive open online courses, or MOOCs as they are called. So the particular MOOC I taught was on the topic of cyber physical systems. And so the topic was much more broader. As MOOCs do, we opened the enrollment to a broad audience, so not just college students in computer science or electrical engineering, but anyone who wanted to learn about cyber physical systems. And we did get an enrollment that was quite broad, as in the usual way, a lot of widespread in ages, going from students that are in middle school and high school all the way to people who were retired and wanted to learn about this. And also, a lot of people who are not computer scientists or electrical engineers by training. And one of the topics that I taught in this roughly 6 to 7 week long online course was formal specification. Like, how do you mathematically specify properties of a cyber physical system? And as we do on campus here at Berkeley, I taught Boolean logic and then its extension to temporal logic. And that was one of the modules, one of the 10 modules in the course. At the end of the course, we did a survey, and we asked the students who were still engaged at that point in time to rank the topics, the various modules that they studied. And to my very pleasant surprise, the module on formal specification, which included Boolean logic and temporal logic, came up as number 3, the top 3 of the theory topics that they liked in the course. And so it's hard to extrapolate too much from this, but I see there's, I was a little, going in, I was a little concerned that this particular topic in the course may seem a little esoteric and less accessible, even to engineers who have been out of college for a while, right? Practicing in industry, and they may feel that there's a lot of notation and it's hard to get past the notation. But I was very pleasantly surprised by the results of this survey. It seems like there is an appetite for logic that's broader than just to mathematicians and computer scientists. That's a fantastic indirect impact of Boole's work.